Good afternoon to all. Today we will see the Schrodinger wave equation for a particle in one-dimensional box and a solution in the form of energy and wave function. Let us consider the one-dimensional box. Let us assume electron with m mass is at x is equal to 0. That is the box wall. Let us. So now this electron is traveling from x is equal to 0 to x is equal to a. Is having both natures, that is particle nature as well as wave nature. And one more thing, we should have certain assumptions or conditions. Otherwise, it is very difficult to solve this Schrodinger equation. What are those assumptions? You see that the conditions for wave function first. If you want to consider your electron as a particle and electron is having a wave nature, for wave nature, we have to consider these three conditions first. Because Schrodinger, theoretically, he has postulated 5 quantum postulates. And from that quantum postulates, we are taking one quantum postulate and we are deriving the solution for energy and wave function. Because it is a complex chemistry, but though directly we can solve it, I will give you the simple way how to solve the Schrodinger wave equation. Prior to that, what are the acceptable conditions or what are the limitations for wave function first? The conditions for acceptable wave function, it must be finite, not infinite. Keep in mind, electron is having particle nature, wave nature with finite thing, not infinite. That means it can go from x is equal to 0 to a, not beyond that. And one more thing, it must be single valued at all the points. If you want to see the value of that at single point, it should have a value. Otherwise, our theory will not applicable, or otherwise our Schrodinger equation will not fulfill those things. Okay, and one more thing is, it should be continuous, and it should have a value and it should be an finite. You keep these three important words. Wave function will be a finite and wave function will be single valued at all the points, and it must be continuous at this is within the boundaries what we are considering. That is what this. You keep this. So let us, if electron is there at x is equal to 0, let us assume this entire thing as an universe. We cannot consider the entire universe as an electron. That is what we are. That means it has an boundary. We have to consider the electron for particular place. That's what we are going for a derivation, that is for one-dimensional Schrodinger wave equation and its solution. Now, the electron will be having two energies. We know well in classical mechanics also, kinetic energy and potential energy. Let us assume inside the box, potential energy 0 or constant, and it will be having kinetic energy inside the box. And outside the box, potential energy will be infinity. That's what the thing. Because outside the box, we cannot go for kinetic energy because we are assuming certain conditions. Electron will not be there outside the thing, and there won't be any kinetic energy, and potential energy will be infinity. That's what 2-3 conditions we are assuming, and we are going for the Schrodinger wave equation solution. As I told you already, we are having standard quantum postulates. From the quantum postulates, quantum postulate 3 will tell us H psi equal to E psi. This is what the Schrodinger wave equation. Here H cap, this is an Hamiltonian operator. It's an operator we are keeping a cap, and psi is a wave function and E is an energy. Now we have to find out what is the energy of electron as well as solution for wave function by using this Hamiltonian operator. This is what Schrodinger equation, and the other conditions are the mass of the electron is m, and the electron is constrained to x is equal to 0 to x is equal to a. And so now we are going to find out the solution for this equation. H psi equal to E psi. H is an Hamiltonian operator, psi is a wave function, and E is an energy. This is equation, let us assume this is equation 1. These are the conditions for wave function. Before going to solve the equation, just we are assuming these are the conditions, or even one side we can tell it is a limitation of the Schrodinger wave equation. And solution to Schrodinger wave equation. If you want to solve this Schrodinger wave equation for any system, here we are applying it for electron. Inside the box, outside the box. There are two possibilities, and the solution can be done, or the solution can be given in two ways. One is, if electron is there inside the box, what is the solution? If electron is there outside the solution, what is the thing? And real solution to this Schrodinger equation is the quantization of energy, that is energy of electron can be calculated, and we are even assuming and we are giving quantum numbers as a solution for the Schrodinger wave equation, and we are going to find out the 0 point energy. That means at first orbit what will be the energy of electron. All these things we are going to determine by this solution. The solution for Schrodinger wave equation is inside the box and outside the box. Let us see first the solution for Schrodinger wave equation outside the box. This Schrodinger wave equation is this one. This is an E is in total energy of the electron, and V is in potential energy. Dou square psi by dou x square plus 8 pi square m by h square into E minus V into psi equal to 0. This is what instead of writing H psi, E psi, just we are writing the Hamiltonian operator, and we are modifying, and we are getting directly one-dimensional equation. This is the Schrodinger wave equation for one-dimensional thing. And since it is not depending on time, this is an independent equation, Schrodinger time independent equation. So now outside the box, V is equal to infinity. Let us substitute this V is equal to infinity in the equation 2. What will happen in the place of V? If you keep potential energy is an infinitive, total energy is very small, because potential energy is infinitive. In this case, what will happen? This entire term will become this infinitive. So now what will be the thing? Dou square psi by dou x square is equal to infinity psi. This is what outside the box, and psi is equal to 0 at all the points outside the box. This is what its meaning. Dou square psi by dou x square is equal to infinity psi means psi is equal to 0. In that case only this equation will be okay, otherwise it will not. So now electron will not be there outside the box by seeing this equation. That's what we can get from outside the box. Solution is electron, probability of finding electron outside the box is 0. Since V is equal to infinitive, and since we are substituting the infinitive in this equation, and the entire thing will become equal to infinity. And one more assumption we can get here. outside the box psi is equal to 0. That is what probability of finding electron will be 0. That is what we can consider, or we can write directly, psi is equal to 0 for outside the box. Next, inside the box. There is one more way, or we are going to solve within the box. Now the same equation within the box, potential energy 0 or constant. We are writing 0, V is equal to 0. If you write V is equal to 0, we are getting, if you are substituting V is equal to 0 in equation 2, we are getting the equation 5. In equation 5 now, dou square psi by dou x square plus 8 pi square m by h square e into psi. This is what the equation we are getting inside the box. Now, in order to simplify the above equation, instead of writing 8 pi square m by h square, simply we are introducing a new term called, new constant called k. That's what, instead of writing that, we are writing k square. K square equal to 8 pi square m by h square. Instead of that entire value or entire term, we are writing k square. Now, dou square psi by dou x square plus k square into psi equal to 0. It is like an quadratic equation. Now it is like an ax square plus a bx plus it is equal to 0. So now we have to find out the solution for psi. That is what an other step now. This next step is we have to find out the solution for psi. Now k square is equal to 8 pi square me by h square is a constant. From this thing, you see here already we are near to solve, near to get the energy, because if this right side term, that is E, capital E, if you want, k square h square by 8 pi square m. That is what the energy of the electron. Here itself we are getting the energy term. So anyway, we have to solve the wave function also. Since it is having a standard equation form, the solution for the psi is e power mx. Now psi is equal to, let us assume the solution for wave function is e power mx. Now if you substitute this e power mx into the equation 7, what will happen? E power mx, if you substitute in equation 7, dou square e power mx by dou x square plus k square into e power mx equal to 0. So now, if you differentiate e power mx, you get m into e power mx. That's what 2 times if you are m square e power mx plus k square e power mx. If you take e power mx as a common, m square plus k square is equal to 0. And we know already the psi cannot be 0 inside the box. Outside the box, psi is equal to 0. That means e power mx cannot be 0. That is what our thing now. Therefore, what we can write? E power mx is not equal to 0. So now what is another chance? M power plus k square should be equal to 0. So now, if you are going to get an m term, what we should, m square is equal to minus k square. Then for minus k square, if you are applying this thing, and it will be a complex number, we have to m, that's what we are writing, plus or minus I. M is equal to plus or minus ik. Now if you substitute this m values, plus ik and minus ik, m is having 2 values here now, plus ik and minus ik. If you substitute this e power ikx and e power minus ikx in psi, that is, and here we should know the one more thing, linear combination of 2 wave functions. That's what we are writing here. Psi is equal to a1 e power plus ikx plus a2 e power minus ikx. For this, we can expand this exponential with respect to cos and sine functions. For that, Instead of writing the equation 9, we are going to write that with respective to cos and sine, that is psi is equal to a1 plus a2 cos kx plus a1 minus a2 I sine kx. This is what the thing, and instead of keeping a1 plus a2, we are writing c, that is a constant, a1 a2 also constant, and a1 a2 are constants. And instead of writing a1 minus a2, we write capital D sine kx. Now a1 a2 c and d are all are constants. Okay. At the walls, what happens? X is equal to 0 and x is equal to a. That is what the boundary of the one-dimensional box. And at the walls, x is equal to 0 and x is equal to a. You keep in mind these two things are there. So now if x is equal to 0, equation 11, whatever we are writing here, cos kx plus sin kx, this CD constants, in that if you substitute this, we will get c is equal to 0. Now c is equal to 0 and x is equal to a at the wall, and on other end x is equal to a and c is equal to 0. If you substitute, and you will get d sine ka equal to 0 and sine ka is equal to 0. When the sine ka will be equal to 0, then ka, if it is becoming n phi only, it will be 0. That's what ka equal to n phi in sine case. Now if you want to find the k is equal to n phi by a. So now this, if you substitute this n phi a value in sine kx, what you get? Sine is equal to d sine n phi by a into x. This is what here, whatever you are getting small n here, that is the quantum number. Then n is equal to 1, 2, 3, 4, 5 only, not 0. If n is equal to 0, what will happen? Psi is equal to 0. That means we are already assuming that inside the box psi is not 0. That means why we are not getting 0 orbit? The reason is this: because inside the box, inside the orbital, there is a probability of finding electron inside. Psi cannot be 0. If psi is 0 means there won't be electron inside the box. That is the meaning. That's what, there is no 0 orbit or 0, n is not, n is 1, 2, 3, 4 only, and beyond that n is not equal to 0. That's what this equation will tell us. Now psi equal to d sine n phi by a into x. Okay, a is the length of the box. That's what x is equal to a. That is what small a here we are writing. So now the solution for Schrodinger wave equation in the form of energy and wave function is k square is equal to 8 pi square me by h square. Now k equal to n phi by j. If you are substituting this k value in that side, and finally you will get E equal to n square pi square h square and 8 pi square ma square. Now this is an n square h square by 8m a square. This is what the energy of the electron within the box. So now for energy we got the solution. For wave function we got the solution. It is nothing but, it's a particle one-dimensional box is nothing but like orbital. Within the orbital, psi is not equal to 0. Out of the orbital, psi is equal to 0. Instead of considering the things, now we don't know the orbital shape and all. That's what we are assuming it is in one-dimensional box. Even the same thing can be applied for even x, y, z with respective to time. Even that is a time-dependent Schrodinger wave equation. It is, and here we have to solve what is this d, what is the value of d. For that, again, if we have to go for a solution, that's what, if you are extending, it is in the solution for this d, you know, we have to go for normalization of the thing psi square, this is 0 point energy. That energy, if you at n is equal to 1, whatever energy you are getting, that is known as 0 point energy. That means the energy of the electron at the first orbit is known as 0 point energy. And we have to solve the D. We have to find the solution for D value. Now, before going to the solving that, psi square equal to 1, psi A inverse equal to 1, like that. And here in quantum postulates, there is one postulate which is telling us psi into psi star equal to 1. According to that, we are going to integrate the psi square. That's what, with the values lower limit 0 and upper limit a, psi square respective to dx equal to 1. That is what that. And we know the psi value now. We know the psi value now. It is in d sine n pi by a into x. That's what now we are squaring that, d square sine square, because psi square. So now this sine square theta we can write, instead of writing 2 sine square theta, we can write directly 1 minus cos 2 theta. This is an if you substitute this basic trigonometric formula into this, instead of writing this, we are writing 2 sine square theta. Instead of writing 2 sine square theta, just we will be dividing this equation with by 2. That means automatically it will be equivalent to 1 minus cos 2 theta. That's what 1 minus cos 2 theta. That's what n phi by a into x into dx equal to 1. Why we are getting 1? This is what a normalization, that psi square equal to 1. Like in matrix, even A inverse equal to 1. Similarly, in quantum postulate, psi star, then inverse of the psi, and the psi, if you multiply, you will get 1. That is what the normalization that we are applying for our wave function equation, and we are integrating the equation with lower limit of 0 and upper limit of j. And if you do the simplification of this thing, what you get finally, just you see that, and if you apply these integration of 0 and j in these values and individually, then you get this equation. And again, if you apply the after integration, if you apply the lower and upper limits, you get this x minus a by 2 n phi sine 2 n phi by a into x. Cos, if you are integrating, you will get sine, and 2 n phi by a will become, this is a by 2 n phi, because it is 1 by you will get, that's what it will be coming, a by 2 n phi. So we know integration of cos and differentiation of these things. If you know the simple this formula, just we can solve this d value. Now this entire thing is equal to 1. Now if you apply the lower limit and upper limit, you see here, instead of x, a we are keeping, instead of x we are keeping lower value 0, and instead of this thing you are get this x term will become 0. So now x only will be the remained term, and instead of x we are substituting the a, d square by 2 into a equal to 1. Now if you want to find out d value, 2 we are sending that side, and d is equal to square root of 2 by a. This is what the solution for wave function. Now instead of d we can write square root of 2 by a. At this point, the solution for wave function is square root of 2 by j into sine n phi by a into x. The n is equal to this principal quantum number here, and we will see what is d and other things maybe in next lecture. Okay, so now we have solved the Schrodinger wave equation, and we have calculated the energy and we have calculated the solution for wave function. Once again, we will see, since it is an important topic, definitely we will see